This problem is from the textbook Conceptual Dynamics. This is example 3.1-6. The problem statement reads, the carriage, shown in the figure, has a vertical slot that is driven in an oscillatory manner such that the carriage's horizontal position as a function of time is x equals 3 times sine of 2t, where x is in centimeters and t is in seconds. This carriage in turn drives the motion of pin A, which is further constrained to move in the parabolic slot, whose shape is described by the function y equals negative x squared, where the y-coordinate also has units of centimeters. Determine the overall velocity of pin A as a function of time. So the first step whenever we solve a problem is to read the statement, maybe multiple times, and make sure we understand what's happening. So looking at the picture, we're told that this horizontal slot moves back in an oscillatory manner. So it moves back according to a sine wave, back and forth. And as it does that, it forces this pin to move back and forth with it. But this pin, not only is it constrained in this slot that's moving, it's also constrained in this vertical slot. So as this moves back and forth, the pin will move back and forth through the slot. And so once we feel like we understand what's happening in the problem, the next thing to do is to identify what's given and what's unknown. So looking at the problem statement, we can see that we're told that the carriage's horizontal position as a function of time is given by x equals 3 times sine 2t. With units of centimeters. And so this tells us the motion of the carriage back and forth. We are also given the function that describes the shape of the parabolic slot. So we are told that is equal to y equals negative x squared, where y is also centimeters. And so it's implied, that these coefficients have units such that the units of x and y come out correctly. Then we are asked to determine the overall velocity of pin A as a function of time. So as pin A is going back and forth through this slot, we want to determine its velocity. So its velocity is a vector. It has components in the x and the y direction. I'll note vectors with this underline. And we need to determine the x component and the y component of the velocity, where I and j are unit vectors, I being in the direction of x and j being in the direction of y. One thing that we'll notice when we describe motion using rectangular or Cartesian coordinates is that since this coordinate frame is fixed, when we differentiate to go from position to velocity, the derivative of the unit vectors is 0. So for example, if we consider the position of pin A, which is what we're interested in, as having some x component and having some y component, we know that velocity is the time derivative of position. So when we differentiate this vector, x is a variable, but I is just like a constant. And so when you differentiate something multiplying a constant, the constant can just come out front. So we get x dot and y dot in the I and j directions. And so this is kind of a convenient thing using rectangular coordinates. And in essence, lets us analyze the x direction and the y direction separately. It's sort of like solving two rectilinear motion problems. So once we've established our understanding of the problem, what's given and what's unknown, we go ahead and attempt to solve the problem. We try to find what's asked for based on what's given. And so here we have, again, a reiteration of what we were given. This x describes the motion of the carriage. But the pin, its x-coordinate is going to be always equal to the x-coordinate of the carriage. So this also describes the x position of the pin. If we perform a little animation, we can see that. So as this carriage moves, its x position is exactly identical to the x position of the particle. And so if we wanted to find the x component of the velocity, we recall that we can just differentiate the x-coordinate with respect to time, where we are told that the x-coordinate is equal to 3 times sine of 2t. Okay. That 3 is a constant, so it's just like it can come out front. When we take the derivative of the sine of 2t, we in essence have to perform the chain rule. We have an outer function, which is a sine, and we have an inner function, 2 times t. If we differentiate the inner function, the derivative of 2t is just 2. And then if we differentiate the outer function, the sine, the derivative of sine is cosine. So that's what the x component of the velocity is equal to. We can multiply the 2 and the 3 to get that. So that's the first part. Now we need to determine the y component of the velocity. Again, the y component of the velocity is just dy dt. When we look at this, we are given what the shape of this parabola is. And so the shape of this parabola tells us how the pin is going to move, how the y-coordinate of the pin is going to change. We may be tempted to just differentiate this and say that it's equal to negative 2x. Negative 2x is actually the derivative of y with respect to x. So it tells us how the y-coordinate changes with respect to the x-coordinate, but it doesn't tell us how the y-coordinate changes with respect to time, and that's what we want. That is, by definition, what velocity is. It's the time rate of change of position. And so in order to determine what the derivative of y is with respect to time, we can use the chain rule again. And one way to think of the chain rule is in this manner. We can think of how y changes with respect to t as how y changes with respect to x times how x changes with respect to time. And so looking at this, you can think of the differential x elements as canceling, leaving us with just dy over dt. Another way to think of this is sort of the derivative of the outer function, the negative x squared, the derivative of that, and then this is the derivative of the inner function. It's the derivative of the x. So looking at this, this is just the derivative of minus x squared with respect to x. When we take the derivative of a polynomial like that, we bring the 2 down. So we have minus 2, and then we subtract 1 off the exponent. We're left with negative x, negative 2x. And then we take the derivative of x with respect to time. And that we actually already have. That we found in the first part of the problem. Substituting in for x, we know that x is 3 sine 2t. So if we expand that out, we have negative 2 times 3 times 6, which is negative 36, times sine of 2t times cosine of 2t. Then we're essentially done. That is the x component of the velocity and the y component of the velocity. You may have an easier time determining how we found the y component of the velocity if we substitute in for x right away. So alternatively, we can think of y as negative x squared, where we know that x is equal to this. So it's negative 3 times sine of 2t squared. So that way, if we take the derivative of dy dt, so again, we have sort of a chain rule. So if we look at this, the outermost function we have is a quadratic, something squared. The next function in we have is a sine, and then the innermost function is 2 times t. And so we can do the chain rule in the same sort of way as we've done before. We'll go ahead and start at the innermost function. The derivative of 2t with respect to time is just 2. So I'll have that negative sign out front. The derivative of the innermost function is 2. Then going in, we have a 3 sine 2t. So keep the 3 out front. The derivative of the sine is cosine. And then the outermost function is the squared. So I'll bring down the 2. And it'll multiply this where we subtract 1 off the exponent. So it becomes this to the 1 power. Okay. And if we expand that out, we get the same thing that we already had. 2 times 3 is 6, times 2 times 3 is 36. Then we have cosine 2t times sine 2t, switching the order. We get the same thing that we already found. It's just a different way to think about the chain rule. So putting everything together, the total velocity of the pin is the x component in the I direction, and then the y component in the j direction. And we know that the length units, the units of x and y, are in centimeters, and the time units are in seconds. So our velocity will have units of centimeters per second. That is our velocity of our pin as it moves back and forth through this slot. And that brings us to the conclusion of this problem.